So I was told that the textbook was out of stock and then it's back in stock again, potentially. So if you're still looking for one, I think that they're in the bookstore. Has anybody seen one in the bookstore lately, like in the last day or two? No? Yeah? Okay, so there are textbooks in the bookstore. If you have not read any of the Grinnell yet, now would be an excellent time to start, because the first writing assignment, which is pretty much all about Grinnell, is due this Thursday. So just a couple quick notes on the first assignment. So again, it's due this Thursday, July 20th. I believe it's due at midnight, Thursday, July 20th, so like just before it turns into July 21st. And there's a 5% late penalty per day, which is not that much really if you need another 24 hours to work on it. It's less than 800 words that you're supposed to be writing, and it's not like deeply creative work. You won't have to go through, you probably won't have to go through 20 drafts to get this perfected. And I expect the average will be reasonably high on this, because we're really just asking you to show that you've been doing the readings, that you've been coming to class, and that you've been thinking about it just a little bit. So this should not be the most challenging assignment of the year by any means. So conceivable to do this one in a day. I would strongly recommend you do not attempt to write your final essay in a day. We can definitely tell when you're doing that, but on this one, you know, a solid day's work should be sufficient to do reasonably well on this, I hope, because we're not going to finish the relevant lectures until the day before it's due, so there's that. I got a couple of pertinent questions on this that probably everybody should hear the answer to. For example, are the word counts strict? My general rule is that a word count has like a plus or minus 10%, an implicit plus or minus 10%. So if you write 220 words, we're not gonna penalize you for it. But beyond about that, you'll start to lose marks on the quality of expression category. There's really only two categories that we're marking you on in this this short written assignment. Quality of expression and your understanding of the concepts. I believe your understanding of the concepts will be weighted more heavily than quality of expression, but we do want you to be writing full sentences, no bullet points, clear, to the point. You've only got 200 words to write these things, so don't waste any words, don't repeat yourself unnecessarily, that kind of thing. And just show us that you understand the material is the main thing. So yeah, plus or minus 10% is fine. Beyond that, you'll start to get dinged slightly on quality of expression. For citations, you do not need, this is not a research project, so you do not need to bring in any external citations. If you're citing something specific that Grinnell said, like he's got this lovely metaphor about 3 different kinds of umpires. So if you want to use the 3 umpires metaphor that Grinnell specifically uses, then you cite the page. Just give me brackets, page number, and that's enough. You don't need to add a bibliography or anything like that. If you want to bring in external citations, that's fine too. Then you do need to give us the author, the year, the page number, and at the end, a complete reference so that we could easily find it. So the point of having a bibliography is so that somebody with library access could find the reference that you're using and check that it says what you said it says. Right? So if you do that, then you've given a successful citation. I don't care too much about the style. But again, that's something that you're allowed to do on this assignment, but not something I particularly recommend. Really, you just want to show that you understand the Grinnell text and the lectures. So bringing in other stuff is a little bit of a risky move because maybe you're showing that you understand something else really nicely, but not necessarily the Grinnell text, and it's really the Grinnell and the lectures that we want you to demonstrate understanding of. Okay? Yeah, question?
Do you need to cite the lectures?
Feel free to. I think if it's something that I said in lecture, you can more or less just help yourself to it. Yeah, so if it's something specific that Grinnell said, please cite the page number, but maybe don't bother citing the lectures. You could say maybe the lecture number or something like that where I said it. Yeah, I don't think you need to. The TAs will have listened to the lecture, so they know what's in it and what's not. So, any other questions about the first written assignment? Okay, good. very briefly, as a general issue, I would like to tell you a short parable about handing stuff in. So whenever you ask a group of more than 100 people to hand something in and give specific conditions on how it should be handed in, you always get, well, the number varies, but people don't follow the instructions, generally speaking. So I've asked that you hand this in .doc, or .docx format only. Some of you will fail to do that. We've agreed that you're going to do blinded, so you're not going to include your name. You're only going to include your student number on the file name and in the file itself. Some of you will also not do that. So I would like to tell you for this and all the other assignments that you'll face in your life, the parable of the brown M&Ms. So just quickly before we get into the class content. Long ago, there was a legendary group of musicians called Van Halen. And they would travel the land far and wide giving these amazing shows. They would have like 4 tractor-trailer trucks full of equipment. They'd put on these huge technical shows back in the days when people didn't really do this. And Van Halen had in their contract this clause, the brown M&M clause, that said, amongst the other things, they had long, thick contracts with all kinds of technical specifications. And in there was this line that said, there will be a bowl of M&Ms in our dressing room, and there shall be no brown M&Ms. None. And if they found a bowl of M&Ms and there was brown M&Ms in it, they had the right to not play the show and keep all the money. Right? So they'd still get paid for the show and they could leave. And this would happen once in a while. They would find either no M&Ms or a bowl with brown M&Ms in it, and they would trash the dressing room and leave and not play the show. And this went around as a story about how terrible Van Halen is. But it was actually a very kind of smart thing to do, because they had this enormous technical show that needed to get everything just right. Like if you didn't give the right amps and watts in the right places, people could die. Equipment would explode, like really bad stuff would happen. So they needed a way to show whether the person had read all of the instructions, taken them all seriously, and taken the time to actually satisfy all of them. So this quick and easy test to see, does this person listen to instructions carefully? Right? So that's the brown M&M clause. Right? They use this cheap and easy test to determine quickly whether the person had actually listened to their instructions. So what I'd like to suggest to you is that there are brown M&M clauses everywhere in your life that you may or may not be aware of. So things like the file format that you submit this in is to us a brown M&M clause. If I say, I want this and only this, and you're like, PDF's fine, that's a glaring sort of like signal to me, like, this person either didn't listen to the instructions or didn't take me seriously. And so all of the little things like that are, from your perspective as somebody handing in the thing, they seem really minor. Right? Oh, they can cope with this. This is fine. But when you're looking at a list of 150 assignments and like 10% of them messed up on a really basic instruction, you kind of automatically classify those as, this person's not going to do very well. Right? Just unconsciously classify them as somebody who's not listening to the instructions. You start off on entirely the wrong foot. Okay, so wherever you go and whatever you do, you will face brown M&M clauses. They won't be obviously marked as such, but they will be there. So keep an eye out for them. Things like file format. If I ask you to have the file have a specific file name, have a specific structure, things like that. Those are all brown M&M clauses. And if you're handing in a resume and you fail some really small but basic instruction, they're looking for the fastest and easiest way to eliminate you. And that'll be a fast and easy way. If you fail a brown M&M clause you didn't realize was there, you're out of the running, like that, no matter how qualified you are. So that's the parable of the brown M&M clause. It's not especially relevant to this class, but I tell it in every time I get the opportunity, because people really struggle with this. This is how lots of people get knocked out of the running for grad school, because they just can't read all of the instructions on the application form and follow them exactly. Lots of people get knocked out of the running for jobs because they can't read all of the instructions carefully and follow them exactly, like more exactly than you think you probably should, kind of thing. Okay. I hope that was mildly entertaining and enlightening. So let's move on to the actual course at hand. Today, of course, we're talking about discovery. This is from chapter 2 of Grinnell, the discovery process in science. And of course, you recall that Grinnell's got this, so he talks about the linear model, which he thinks is an incorrect model. He thinks is the model that's inadequate for the actually describing science. And what he wants is for you to replace your linear model with this sort of two conversations model, or the cyclical model, he calls it. So the cyclical model of science, where there's a discovery process, which is an interaction between the individual scientist or a small group of scientists and the world, and then a credibility process, where we take the things that an individual scientist or a group of scientists say and try to decide whether they're reliable information or not. Today, of course, we're doing discovery, and Wednesday we'll do credibility. So I want to flag, the point of this lecture is to show you, so what I promised was that I'd show you how values can be actually operative in science, and this is in the discovery process. We're not going to be talking about, here we're not going to be talking about values as you would usually use them. So I did a bunch of elaborate setup about values so that this would make sense to you, what we're going to talk about today, really. Usually, when you talk about values, you're talking about things like moral goodness and uprightness and all of that good stuff. That's really not what we're going to be talking about today. We're going to be talking about another type of value judgment, which is that something is interesting, relevant, or important. So this is also a kind of value judgment, but it's a very specific type of value judgment, right? So it's a kind of, and I think it's probably the kind of value judgment that you'll see most operative in science most of the time. So picking out something as interesting, picking out something as important and therefore worth studying is a kind of value judgment. It's what I'm going to try to convince you of today, and that it's one of the most important value judgments that you're going to make in your career as a scientist. That's certainly what Grinnell's going to try to argue. So again, when questions, and so again, it's not the case that Grinnell thinks that values are always operative in every bit of thinking and reasoning that you do as a scientist. There are lots of cases where values just don't, there's no role for them to play. For example, when a question is extremely well defined, and I'll talk a little bit more about these concepts at the end, pardon me. But so, and very well, the argument basically here is very well-defined questions, there's no role for values to play. But when questions are ill-defined, we need to decide what to ignore and what to pay attention to. So there's this cognitive act that underwrites all of our coping with ill-defined problems. Ill-defined problems, like the first writing assignment is an ill-defined problem, because what exactly does success look like? It's not clear. So that means that you have to decide which parts of the text you're going to focus on, which parts you're going to ignore. And that's a decision about what's important, what's relevant, what's interesting, what's central. These are the kind of value judgments we're going to talk about today. So Grinnell goes through a number of examples. Sometimes noticing things, so deciding what to pay attention to, is actually dead easy. So for example, the drug UK 94480, really catchy name, was originally tested as a chest pain medication, but during trials, another effect was noticed. Men reported having several hour-long erections. This was not a hard side effect to pinpoint. They noticed very quickly. This happens when you have a multi-hour erection. You tend to notice that kind of thing. It jumps out at you, as it were. So this is Viagra, right? They discovered Viagra by accident. They were testing it for something else, and then the men who used it reported this very distinctive side effect. And I would propose that this is the kind of ultra easy example of noticing things that were outside of your research program, outside of your direct research program. So it's super duper easy to notice things when you're like, I'm going to run an experiment to see if this has an effect on chest pain. And probably it's not that hard to tell whether it has an effect on chest pain. Noticing byproducts, side effects, and unexpected results is a little bit harder. This is an easy case, right? Typically easy case. Grinnell spends most of this chapter, or much of this chapter, talking about a case study that I really like because it's a kind of small-scale scientific quest, right? This isn't the case of, Einstein overthrowing Newton and bringing in a whole new language and a whole new set of formalisms. This is Grinnell navigating kind of medium-sized questions in cell biology and having to do this interesting act of noticing something unexpected, deciding that it wasn't just a piece of noise, but actually an interesting enough phenomenon to shift and start studying. Okay? So what he was studying originally was cell metabolism, so he's trying to understand how within the cell it works. And the experiment involved having cells in a petri dish. I think there were liver cells, rat liver cells, in a petri dish. And to perform his experiment, what he needed was for the cells to adhere to the petri dish. They needed to stick, or else he couldn't run his experiment. And under one experimental condition, he found that they weren't sticking. They would come apart and float around in the medium. Right? So for him, this was a problem with his experimental method. And the standard thing to do, the normal thing to do when you come up with a problem in your experiment is to just fix it. Right? You don't ask, well, what's the deep underlying significance of this problem? You say, how do I get rid of it? But Grinnell, in this specific case, thought that this was actually fairly interesting. So what he did was he switched projects, right? He said, okay, instead of asking about this thing we were doing in cell metabolism, let's ask about cell adhesion. So one of the important things that your cells do is stick together, right? Like if they didn't adhere to each other, you would just fall apart into a goo. So cell adhesion, this incredibly important thing that cells do, was also an area of study. Right? There was also people asking questions about how do cells adhere to each other, like what specific molecules are involved, how much of them need to be there, under what conditions do they do their job properly, and so on. So cell adhesion was itself an object of study, and what Grinnell did was take this bit of kind of experimental failure and say, oh, well, what if the failure under these conditions is actually illuminating for this other research project? Right? So he's taken a piece of noise, an error, and he's transformed it by rethinking about it, by changing the way he saw it and understood it. He was able to turn it into a new research program, or a new research project at least. And this is a serious value judgment, a really serious value judgment, partly because it's a risky judgment to make, right? So he had to, you're all set up, you've got a procedure going, you got a grant to do a thing, you got an experimental setup in your lab, and changing projects means basically throwing out all of the work that you've done so far and saying, all that prep work gets kind of put aside, and you have to completely retool your experimental setup. You have to read a whole bunch of background papers now. Like you have to re-educate yourself. You have to physically retool your lab. You have to convince whoever's funding you. You have to convince whoever's funding you to like keep funding you on this new direction that you've taken. So switching projects midstream is by far not a trivial thing to do. And the judgment that he had to make was that the opportunity that this new thing that he'd found represented was tempting enough, was interesting enough, and potentially rewarding enough to throw out a bunch of work that he'd already done, completely retool his project. So that's the sense in which this is a value judgment. So you're under conditions of considerable uncertainty, deciding when it's worth your while to give up on a whole bunch of work that you've done, like massive, massive amounts of work, massive amounts of prep work, and shift gears. Okay. So, but what happened when he did this, so he's recounting this presumably because this was a good idea on his part. What happened when he did this, made this shift, was a whole bunch of new things started appearing, right? Having moved to cell adhesion, new experimental questions presented themselves, and new methods became available. New experimental techniques started becoming relevant to him. It's a whole new ways of thinking about this. It's the same cells, probably they weren't exactly the same cells, but like you're still working with cells in a petri dish, the same object that you're investigating, but now you're taking a whole new perspective on it. And doing this, I think it's worth noting that doing this as a junior scientist, so making this kind of shift is okay if you're extremely well established and have a great reputation or something, like you've already won a Nobel Prize or something. But as a junior scientist, you don't really get to just kind of say, well, something really weird happened in the lab today, and now I'm going to spend the next 4 years of my life studying it, unless you can make a really plausible case for why that opportunity is going to be worth your while. And in Grinnell's case, that was it was an all right case to make. Like, you could make that case because people were already studying cell adhesion. So there's a kind of pre-existing literature on it. There's a pre-existing set of experimental techniques. There were people you could ask about it, and you could ask, like, hey, I've got this idea. Do you think this is going to be worthwhile? And so his more senior people in the lab got to connect with other researchers and say, okay, is this promising? Is it promising enough for us to dump a whole bunch of work and start up a whole new set of work? So he was shifting paradigms, you could say, but he wasn't creating a whole new one for himself. He was moving from one to the other. Nonetheless, it was an example, a really nice example of seeing something in a totally new way and transforming it by seeing it differently, by doing this really interesting behavioral act that humans are capable of, noticing something novel, noticing something that nobody had noticed before. He was able to bring out a whole new set of interesting facts. And the shift that he made from one problem to another also included sort of like a continuing shift. So even after he'd shifted from the question of cell metabolism to cell adhesion, he still had to continue to shift which questions he thought were relevant. So for his example is, he started off thinking that cell count was the important thing. So the question is, how many cells stick to the Petri dish? And his methodology at first was just count the cells. Count how many stuck and how many didn't under various conditions, and that'll give you insight into cell adhesion. So he was thinking, at least still partly thinking with his old experimental toolkit, but the more and more he got into the literature and the more he connected with other scientists who were familiar with this stuff and had different ideas about what might be relevant, he came to this new sort of methodology, new set of things that were worth noticing. Specifically, he started thinking about the shape of the cells. Right? So if you think that the shape of the cells is relevant to this question, and people who are doing cell adhesion did, then you can't just count the cells. You have to actually take photos of them, right? You have to see what shape they are. And suddenly what was data, once again, what was data, the number of cells that stuck, became irrelevant. And something that was irrelevant became data. That is, the shape of the cells didn't used to be. So he didn't used to pay attention to the shape of cells at all, just the count. And then he shifted. So just the shape became relevant, and the count was something that he started to ignore. Huh? So this is the process that a scientist goes through, Grinnell claims, of, you don't just notice everything. You don't just pay attention to everything. Doing this stuff means selecting what's important, what's interesting, and focusing on that to the exclusion of everything else. The second half of this lecture, I'm actually going to make the case that this is not just scientists, but this is the general condition for humans who have to think in conditions of vagary and uncertainty, which is like almost all the time. Yeah? Okay. So that's Grinnell's example, as his sort of central example in this chapter of how discovery involves values. And it involves values in the sense of values about what's important or interesting in a context. And what we saw was he's moving from one set of views about what's important to another set of views to yet another set of views. And so he's shifting what he thinks is important and relevant in a context according to basically different sort of mini paradigms, so like different ways, different collections of experimental methods and techniques. A bunch of philosophers have articulated the kind of thing that he's talking about here, and one of them is Ludwig Fleck, who talks about thought styles and thought collectives. So every individual scientist probably has their own unique thought style, right? There's things that jump out at you that might not jump out at anybody else in the world. There's Humans are very complicated, and relative to our degree of complexity, there's not that many of us, so it actually is plausible that your way of thinking is unique on the planet. If you get into the detail, like roughly speaking, we're all more or less the same, but if you got into the details, your thought style is based on things like your experience, your upbringing, which books you've read, what you feel about the world. All of that feeds into your thought style as an individual. But of course, scientists never interact with the world just strictly as individuals. Not anymore, anyway. So what we have are thought collectives. That is, we organize ourselves into communities. All humans do this, but scientists as well. Organize themselves into communities where we share between each other perspectives on what's important or what's interesting. So a thought collective is a kind of relatively uniform set of things that a group or a community agrees are important and interesting. So you as an individual have this wide possibility of variation in your cognitive style. A thought collective is a group that at least shares one collection of thought styles. Probably they don't share all of their thought styles, like they like different kinds of music, and maybe they have different interests in their extra scientific life, but to the degree that it's a scientific community, it's a community because they share sort of at least parts of their thinking styles. They share at least partly how they think about what's important or is interesting. Probably the more famous version of this is Thomas Kuhn's notion of paradigms. Has everybody heard of paradigms, at least heard the word? I hope so. I hope you've heard this notion before. It's kind of like this idea was more or less at the founding moment of what's called history and philosophy of science, where we try to bring history and philosophy together. So this is important in the HPS world. So Thomas Kuhn talks about scientific paradigms. What I'd like to warn you about this concept is that it gets used in a lot of different ways. A lot of different things are meant by the word paradigm, even within Kuhn's book. So we're going to try to narrow it down how we're going to use it in this class so that we have a useful subset of that. What I would like to use the word paradigm for here is, this is a shorthand, but temporary solutions to the problem of noticing. So you've got this problem, the problem of what to notice. You're in this information-rich environment. You've got finite cognitive capacities to deal with it, so you have to pick out what's important and what's interesting and what gets ignored. And a paradigm, I would like to suggest, is like a thought community's collective, temporary solution to that problem. Say, okay, people, here's what we're going to notice. Here's what we're going to pick out as important, interesting, or relevant. Here are furthermore the kinds of experiments that are the good ones for finding out facts about that. Here is the kind of statistical practices that are good for applying to this area. So it's a collection of views, ideas, and methods that together help you solve, at least temporarily, this problem of, in this context, what is it that I should notice? Is that at least somewhat clear? I mean, some other ways that this word get used are a paradigm case is like a really typical case. And the connection with this sense of that is like there's a paradigm experiment. So somebody does a really clever experiment that everybody kind of builds off of, right? So that's a paradigm case that everybody's got the same, not exactly the same experiment that they're running, but they take one really typical example, typically a really successful experiment, and then they do a variety of variations on it because this is sort of shown that it can be successful. Again, I would like to warn you that even Kuhn uses this word a bunch of different ways, so it's one of those unreliable words. If you think you know what somebody means by it, it's probably safer to ask to get them to use a different word because it's just incredibly polysemic is the word for it. It has many meanings. Okay. So again, temporary solution to the problem of noticing. So paradigms or collective thought styles, the thought styles shared by a thought collective, provide a lens through which to see this world, see the world. And the binocular metaphor is really apt here because a lens, in this sense, the binocular lens, really enhances the thing within your field of vision. Right? You can see a lot more about it through the lens than you can through your naked eye. But it also excludes everything outside of your field of vision. Right? It's precisely this trade-off that you get between clarity through exclusion. Binoculars do this, and I would argue that paradigms do this as well. Right? They pick out, because they help you solve the problem of noticing, they convince you, at least temporarily, that everything outside of the paradigm is nonsense or noise or irrelevant. Something like this. It's blinding in that sense. A paradigm is blinding to almost everything. But that's actually what you want. That's what you need, is to be blind to almost everything. Because you can't pay attention to everything. So the binoculars are a really nice metaphor for this. They provide clarity of vision, but only straight ahead and only in this very limited field of view. The problem is, as humans, we don't have the option of having no binoculars. Like, you've got one set of lenses or other, and there's not really an option to be like, I'd just like to see everything all at once. It doesn't really work. Okay. So Grinnell's got a nice kind of, well, he's got a nice method for clarifying how paradigms are helpful, and it's through this kind of odd route of Plato's supposed paradox of discovery. So he says, conceptually speaking, we should say discovery, according to Plato, discovery is impossible for the following reasons. So a man cannot search either for what he knows or for what he does not know. He cannot search for what he knows, since he knows it, and there is no need to search, nor for what he does not know, for he does not know what to look for. So you can never discover anything. Haha. What do you think? So you can't look for anything that you don't know, because if you don't know it, you don't know what you're looking for. And if you do know it, then you can't learn anything new about it. You already knew it. Yeah?
He doesn't account for things you can just happen to stumble upon.
So he doesn't account for things that you can happen to stumble upon. But if you just stumble upon it, then you won't know what it is, unless you already knew what it was.
That's what you look for.
Sorry?
That's what you look for.
That's what you look for. You look for the.
Why it is.
Interesting. Okay, there's another comment up here. Yeah.
I'd like to reference Plato's Symposium.
Okay.
In Agathon's portion, Socrates questions him whether what is not good is bad, and he affirms it in Agathon's portion. When we get to Socrates' speech, his conversation with Agathon actually infers that there is a middle area between what is good and what is bad. So I assume in this instance there's something that is between knowing what you know and what you do not know, and that is the area that it discovers.
Excellent. And extremely erudite version of this. So it might be the case, the way out of this paradox, and I think this is what you were driving at as well, somewhat. So the way out of this paradox is very likely to say, you can't just divide the world into things that are known and unknown as a strict binary. That's a silly way of dividing the world. And this is the way you get out of a lot of paradoxes, like the paradox of the heap. So like 1 grain of sand is not a heap. Adding 1 grain of sand does not turn a non-heap into a heap. Therefore, no matter how many grains of sand you sprinkle, you'll never get a heap of sand. The answer is, of course, to not be so binary about everything. Admit that there are degrees between things, right? So there are degrees between knowing something and not knowing something. And this is exactly the solution that I think somebody like Kuhn and somebody like Grinnell will suggest. They say paradigms are not fixed and eternal, right? So we don't just say you definitely have things that are within the paradigm and things that are outside of the paradigm, and there's just a clear split between them. Their details shift gradually, so what we think is interesting can be disputed and can slowly shift. And sometimes we go through big revolutions. So we go through big conceptual changes within paradigms, or sort of between paradigms, right? So the absolutely classic one is, we used to think the world was Newtonian, which meant a whole bunch of specific things, like there's absolute space, and space doesn't change. And then we went to sort of both general relativity and quantum mechanics, where all of the assumptions of Newton were overthrown. So those are classic examples of big conceptual revolutions. We saw within Grinnell's example that he was doing a kind of similar thing at a micro level. So he's going from one way of seeing and thinking to another. He wasn't necessarily breaking completely new ground, but moving kind of small scale paradigm shifts. And the solution here is precisely to accept the idea of gradual conceptual change, and that concepts develop gradually. Dark matter and dark energy are my favorite examples of this, because when we first came up with the, I keep saying we as though I'm like a scientist, the general we. So when scientists first came up with the concept of dark matter and dark energy, they were really just labels for our ignorance. They were just massive, so galaxies weren't moving right. Galaxies were moving around as though there was 10 times more mass in them than we could observe. And that was just a big problem in our models. So they stuck the words dark matter and dark energy on those phenomena. So we observed this thing. We stumbled across something. We're like, what is that? What's going on? None of our sort of conceptual tools give us any purchase on understanding what we're seeing here. We just stuck a label on it, dark matter, dark energy. But over the last, I don't know how long we've been studying this stuff, but like decades or so, we're getting more and more purchase on these things. So you've got maps of where we think the dark matter is in the universe, right? So we don't know what it is. There's no satisfying account of dark matter or dark energy, but we can tell where it is. And that's progress, right? That's a little bit of progress in filling out these concepts, turning them from something that was just a label for ignorance into something that's a sort of positive, clear concept of something. Hopefully this process continues, and eventually we'll know, we probably won't call it dark matter anymore once you can shine a light on it and see it. But these conceptual categories started off as really empty, just a label for not knowing what the heck is going on, and then gradually over time are becoming full-blown concepts that can be applied in the world and tested for. We're building dark matter detectors because we have a couple of guesses about what they might be, what the stuff might be. So this is how concepts often go, right? They start off as just I don't even know what this is. We'll stick a label on it. And then slowly but surely, properties get attached to that label until you get a full-blown scientific concept. So this is the solution to the problem of noticing, of course, to admit that there are lots of degrees between having something within the scientific view, or sort of having a paradigm that explains something, and not having a paradigm that explains something, is that there's just a wide sort of set of degrees between those two things. So sometimes your way of separating the world sometimes your paradigm does matter, and sometimes it kind of doesn't. Sometimes separating the world into relevant and irrelevant bits is a really hard problem that you must solve. Sometimes what's relevant is just completely obvious. And we'll talk about well-defined and ill-defined problems. I propose to take a 10-minute break now before we get into this, so you're fresh when we start. Okay, it's 11, so let's start again. Right. So we were talking about the conditions under which your values are potentially going to play a role, and conditions under which they're not. And my argument for today is that for the specific sense of values, the sense of important or relevant or interesting, here are the conditions under which something is possibly value-laden and the conditions under which it is not. So something is a well-defined problem, like tic-tac-toe. Your values really don't play a role in solving the problem. Suppose the problem you're trying to solve is how to win a game of tic-tac-toe. Really, your values are going to be irrelevant. because it's a solved game. Like the complete set of possible moves in this game is well specified. The goal state is well specified, and so you don't really, there's no distinctive styles of, nobody watches tic-tac-toe tournaments and goes, ah, his style is just so brilliant and effervescent or anything like that. Now compare that type of problem to an ill-defined problem, like raising a child. Raising a child is an incredibly ill-defined problem, because what does success even look like? Right? So well-defined problem has a clear goal state, and the set of possible actions that you can take to move yourself towards that goal state are also clearly defined. Relatively small, you know all of them. There are 9 places that you can place either an X or an O. That's it. Those are the only actions you can take to bring yourself closer to your goal in this context. And you know, I mean, if you work out it doesn't take long to figure out which moves will take you closer or further away from your goal. It's a very well-defined problem. No place really for values to play any role. Right? There's no problem of noticing here. There's no problem of noticing what's relevant, because you just notice everything, right? You notice what's happening in all of the 9 possible move locations, and that's it. That's how you play tic-tac-toe. Now, compare that to raising a child. There's a very unclear goal state. Right? What does success look like when you're raising a child? Different people have different goals. Like probably your parents have some notion or other of what success would look like in raising you, but it's certainly not like tic-tac-toe, where you just know completely yes or no. Did I win this game of tic-tac-toe or didn't I? Somebody try to raise a child, success or failure is very vague and ambiguous. It's very unclear what would count as success. Like if they spend 4 years semi-homeless as a poet, did you fail to get them launched on a career, or did you succeed in letting them really embrace what they find is interesting and important in life? And probably most people consider both of those to be important, like social and economic standing versus personal satisfaction and fulfillment. And it's not obvious which of them is the more important one in any given case. It should be obvious. Tons of ambiguity when you're raising a kid. Furthermore, the space of possible interventions is enormous, right? The set of things that you can do to or for a child as you're raising them is ridiculously large. For example, it includes all of the possible sentences that you can say to them, which is astronomically huge. Actually, that space makes astronomical things look tiny by comparison, right? It's humongous how many different grammatical sentences you could produce, and you have to choose amongst those sentences over the 20 years or so of their childhood, which of them you're gonna say to them. So that's already a big one, and that's not even including, that's just the things that you can say to them, never mind the things that you can do for them, or with them, or to them, right? So the set of actions that you have available to you vastly, vastly outstrips your capacity to do them all by any means, and so you have to select from this enormous space of possibilities which ones you're actually going to realize, and you have to do that without really knowing how they're going to affect the child, and without really knowing what your goal is. So this is in a tremendously ill-defined problem. And here, you face the problem of noticing, right? You face the problem of deciding what's important to pay attention to and what you should ignore. So those are ill-defined and well-defined problems. I'd like to talk for a little while now about the frame problem. This is the best thing I learned in my undergraduate degree, so I thought I would share it with you. If you find this stuff interesting, by the way, the stuff I'm going to talk about for the remainder of this lecture, you should take Intro to Cognitive Science here at U of T. It's a great course. It's the best course I took in my undergrad, I would say. And the frame problem is kind of a central problem in that course. So in the 60s and 70s, when we first started the problem of creating artificial intelligences, people thought that it would be a fairly straightforward programming problem. Like, here's how reasoning works. You have a bunch of rules, you apply the rules, and that's it. So if you just program at a computer enough conditionals, so if you face this situation, do this. If you face that situation, do that. And it just looked like a problem of just writing down enough rules. You write down the rules of reasoning, you program logic into it, and that would be it. They said 10, 15 years, we'll have artificial intelligence. It's going to be great. Turns out, not so much. We're still working on it, right? And we have really good artificial intelligences if what you can do is put a nice frame around the problem for it, right? So chess computers got better than humans at playing chess in like, was it the late 90s or something like that, when Deep Blue was late 90s, early 2000s or something, when Deep Blue beat Garry Kasparov. So if you can tell it, here are the moves available to you, here's the goal state, and here are how the moves relate to the goal state, then you've put a frame around the problem. You've turned the problem into a well-defined problem, and then we get really good traction on it using AI. Okay, so here's something that an AI still currently cannot do. Read a 12-page paper and summarize the important parts. You humans are the only things on this planet that can currently do that task, for now. I'll have to revise this lecture next year to see whether they've gotten that far yet. But currently, we're the only things that are able to do this, where we're able to sort what's relevant from what's irrelevant. And that task, that sorting of relevant from irrelevant, is the task of intelligently ignoring almost all of the universe, almost all of the time. It's the foundation of your intelligence. Right? That's the thing that distinguishes you from a computer, and it's the most interesting thing about you, is the capacity to ignore almost everything almost all the time. It's not something that makes you dumb, that's what makes you smart. Okay? And let's do a nice example. So this is from a lovely paper called Cognitive Wheels, The Frame Problem of AI by Dan Dennett. I put it up on the Blackboard under this week's stuff as an optional reading. I want to emphasize that the optional readings are not on the test. Okay, so I'll throw up optional readings occasionally. If you're interested in more of this, please read this paper. Please take Intro to CogSci, because they're fascinating. So here's Daniel Dennett's classic explanation of the frame problem in AI. We've got this robot. Call him R1. Call it R1. The robots don't have genders as far as I know. It's pretty smart. It's reasonably smart. It knows that it needs batteries. Right? It runs on batteries, and you put it in a room with a battery on a wagon. And there's also a bomb on the wagon, a time bomb ticking away, about to explode. And R1 goes, aha, a battery. I love batteries. So it pulls the wagon along and explodes and dies. You say, well, this robot was fairly clever, just not quite clever enough. We need to upgrade it. So we build R1D1, Robot 1 Deducer 1. So it's able to deduce the side effects of its actions. Yeah? So great. Now you put it in a room with a wagon and a battery and a bomb on the wagon, and it freezes. And the bomb goes off. It explodes. So you go and check, and what was it doing when it froze? Well, it was deducing things. So it was deducing things like the side effects of its actions. Like, I want to get that battery. What if I pull the wagon? What happens then? So we said we needed to deduce the side effects of our actions, not just the effects of our actions. So it's deducing things like, if I pull the wagon, its position relative to Venus will change. If I pull the wagon, its position relative to Mars will change. If I pull the wagon, its wheels will turn at roughly the same rate. If I pull the wagon, the stock market will be unaffected. If I pull the wagon, and so on and so on and so on. Because the side effects of any action are this infinite list, right? So it's just crunching through this infinite list of side effects. And it will never finish that task. It will never finish the task of determining the complete set of all the side effects. Say, okay. We get it now. What we need is not just a robot that can deduce the side effects of its actions, but a robot that can tell which side effects are relevant and which are irrelevant. Haha, solved it, right? So now we do R1D2. R1D2 is put in the room with the bomb and the battery and the wagon, and it likewise freezes. Stands there until the bomb goes off and kills it. And you go and look at its processing, try to figure out what went wrong. And it's, once again, if I pull the wagon, then the left wheel will change its position relative to Venus. Irrelevant. If I pull the wagon, the right wheel will change its position relative to Venus. Irrelevant. If I pull the wagon, it will change its position relative to this room. Irrelevant. Right? So it's still calculating all of the side effects, but now it has an additional task of listing either relevant or irrelevant beside them. So deducing side effects is fine, but deducing them all and then marking them as relevant or irrelevant cannot be the solution to this problem. What you need is R2D2, who is somehow able to not only deduce the relevant side effects, but to actually ignore the irrelevant ones, to not have to do the deduction. This is going to be true anytime you're dealing with an ill-defined problem with a large search space and finite cognitive resources. And guess what? That's all of us, most of the time. So that's any finite agent dealing with a complicated world and limited cognitive resources is going to have to do this somehow. And nobody's quite sure how we do it. Right? How do you put a frame around the universe such that what is inside the frame is the important stuff, and what's outside of the frame, you can not only see it and mark it as irrelevant, but you can actively ignore it, not even consider it, not even have to use up some of your very limited cognitive resources to mark it as irrelevant. It could be the case that some of the stuff that in the frame gets also marked as irrelevant, but so long as it's a nice, clean, limited set, that's okay. Right? So sometimes something can look relevant, and you're like, oh, okay, geez, well, that turned out not to be relevant, that's fine. But you do need some way of starting from a limited set, a very limited set, a very small set of things that are potentially relevant. And the lesson of the story is supposed to be, you can't do that by first looking at all of the facts and then paring it down. That's just not going to work, because the potentially relevant facts are infinite. At the very least, it's vastly, vastly larger than you have any capacity to deal with. Like, for example, you can't build a chess computer that can look at all of the possible moves in chess, because the possible moves, there's trouble calculating the actual number of possible moves, but it's something on the order of like 10 to the 40, so 10 with 40 zeros after it, possible moves, which is substantially more than the number of atoms on Earth, certainly. I think it's more than the number of atoms in the visible universe. No, it's not. I don't remember. Anyway, 10 to the 40 is just way too large to build any computer, as far as we understand that term, that could look at all of the possibilities. You have to give even a chess computer where the problem is reasonably well-defined, like way more well-defined, for example, than your first writing assignment. That problem is reasonably well-defined, and nonetheless, we have to give it a bunch of rough and ready rules, heuristics, strategies, ways of sort of automatically treating things as irrelevant. Okay, so there you have it. That's the frame problem. It's a problem that became salient when we started taking seriously the idea of building minds, right? And it didn't appear to us, like in the 60s and 70s, in the artificial intelligence days, this problem didn't jump out at people, right? They thought, reasoning is applying rules. There's a relatively limited set of rules. We just program them into a computer, and now you've got a reasoner. This problem of dealing with finite cognitive resources really only became salient to people when they started really trying seriously to build computers. Sorry, not build computers, build artificial intelligences. Any questions about the frame problem? Okay, that's the best thing I learned in my undergraduate degree. This is my favorite thing, because it's such a deep problem, and even saying it sounds like you're saying a paradox. Like intelligently ignoring sounds like a paradox, right? It's typical to think of information like. I think it's typical to think about rationality as gaining as much knowledge as you can, but that turns out to be really a losing strategy. Like, and especially, I mean, more and more every day, as more and more information becomes available to every one of us at this like lightning pace, the search space becomes bigger and bigger every day. So the frame problem that we're facing gets larger and hairier with every passing day. You kind of feel jealous about people back when there was only like 50 books in the world. And if you wanted to know something, you went and read one of them. And then when you read all of them, that was it. You know all the things now. That is certainly not the case that we find ourselves in. And it's probably the frame problem has always been with us implicitly. Somehow the problem is not that it's impossible to do this, because we obviously do this every day. You ignore almost everything in your environment, and you hone in on a bunch of stuff that's relevant. So each of us solves this in the sense that we have some way or other of doing this. Just currently nobody knows how. If you can figure it out, you can be a trillionaire and replace the human race with a race of super intelligent robots. I don't know if I'm rooting for you on that project or not. All right. So the point for us is that this frame problem so in tic-tac-toe, there's not really a frame problem, is there? You can bring the whole thing within the frame. Right? You can get all the relevant information in your frame. You can check all the relevant information because there isn't that much of it. Raising babies, you got a monster of a frame problem, because it's really not clear what's going to be relevant. And if you try to specify that beforehand, especially in 2017, like if your parents are applying the frame that they got as children in 2017, the frame is not going to fit, right? There's going to be a bunch of stuff that didn't used to be relevant that's relevant now. There's a bunch of stuff that used to be relevant that's not relevant now. My grandfather recommended that it was very important that I learn how to play bridge, because that's how everybody socializes in the world. They get together and they play bridge. That turns out to be not all that relevant. That was in his frame, turns out is not in the frame anymore, generally speaking. And then there's this wide middle ground of problems that are highly complex, maybe not infinitely complex, like there are a finite number of moves in chess, right? Assuming that you don't have infinitely long games. But for any finite length of game, there's a finite set of moves in chess, possible moves that match the rules. Nonetheless, it's too big of a space to exhaustively search it. Like you can exhaustively search the tic-tac-toe problem space. You cannot exhaustively search the chess problem space, so you face something of a frame problem. It's a medium level frame problem here. But the fact that we've been able to get computers to be vastly better than any human shows that this is not that bad of a frame problem, right? So it is possible to specify in advance what's relevant and what's irrelevant if all you're trying to do is put the king in checkmate. So I would suggest that science is somewhere between chess and child rearing, I would suggest, lies science, generally speaking. For those parts of a scientific process that are extremely well worked out, they can be like tic-tac-toe, where it's just like, no, we just know what's important here. But especially the process of scientific discovery, I think, and Grinnell would probably put it the same way, somewhere between chess and child rearing, because it's not obvious in advance what's going to be important. It's not obvious in advance what success will look like. And that was what the cell metabolism to cell adhesion story is supposed to show. So again, we'll go back to paradigms as temporary solutions to this. So a paradigm constrains, so a paradigm in the sense, a few more meanings of the word paradigm here. So Kuhn talks about paradigms in terms of not just sets of typical examples, but as beliefs about like the nature of the thing that you're talking about. So the paradigm in psychology for a long time was behaviorism. Behaviorism was the belief that you can describe a psychological phenomenon just in terms of inputs and outputs. So if you feed the rat, it'll behave thus and so. If you shock the rat, it'll behave thus and so. So you just measure the inputs and the outputs, and that's all that's important or interesting about psychology is the effect of stimulus on behavior. So that was behaviorism, popular for a lot of the 20th century in psychology. It's less popular now. That's no longer the dominant paradigm in psychology because people started to take seriously the idea that you have internal states that matter. So like the psychology of the rat, the internal process of the thing that you're studying actually matters. So that's a new set of things that are interesting and important in that field of study. And so a paradigm is, for our purposes, a set of things that a group of scientists think are important or interesting and a set of ways of trying to get at them. So it's a goal state and a set of, so you specify the goal of your research, and furthermore you specify the moves that you can make to achieve that goal. So what kind of experiments would be the right ones to tell you about that goal? You know, what kind of methods are interesting and important to bring you closer to understanding that thing that you set as your goal. So I like the Lego piece metaphor for this. A paradigm is like a bucket of Lego pieces, right? So in some sense, you've been given a prefabricated set of things to play with. You can put them together in a variety of unique ways, and you can also add in new pieces sometimes or take away pieces. Like there can be a gradual shift in maybe a new experimental technique shows itself to be really worthwhile, and you add it into your paradigm as a gradual paradigm change. Or sometimes you throw the whole thing out and bring in a whole new set of pieces, and that's a paradigm shift. So the paradigm is like, for whatever your discipline is, the paradigm is is a collection of accepted goals and ways of getting at those goals. Usually experimental methods. You can add things like, so contemporary climate science, for example, has a paradigm, and that paradigm includes things like satellite imaging. That's a good way of getting data. They've got ground measurements. That's another way of getting data. They've also got simulation experiments. It's a relatively new way of getting data about climate, right? So this is a new puzzle piece, a new Lego piece being added into their collection, out of which you can build new things. Okay? Right. So just to connect this to a couple of other ideas in psychology, what Grinnell wants to suggest is that science is often an insight problem. It often provides us what are called insight problems, where the problem is not how to use the pieces that I've been given. The problem is that you've misframed the situation from the beginning. So here's a really classic piece of research on what's called insight problem solving. It's called the mutilated chessboard. So what they did was they got a bunch of psych students, first and second year psych students, as they always do, and brought them in and showed them this picture and said, okay, can you tell me whether it's possible to cover this board entirely with like dominoes, and a domino will cover two squares, right? So there's these two, if you got little tiles that are 2 squares wide, can you cover this board so that you cover all of the pieces but with no overlap? There's nothing hanging over. Right? And so the way that people usually frame this is a tiling problem. So you start imagining like, okay, I'll put one here and one here and one here. Oh, there's a thing here. Okay, so I'll put one vertical. Okay, then that means I can put one here and one here. And okay, well, so they frame it as a tiling problem, right? You're all working away at this. But the problem is the space of possible ways of laying tiles on this thing is really big, really big. Apparently one research subject filled like notebooks full of like trying to prove mathematically that there is a tiling that works. But there's a much nicer solution. So if you frame this not as a tiling problem, but as a different kind of problem, there's a really nice, quick solution. Anybody who hasn't seen this before? Yeah. Oh, you've seen it before. Okay. Okay. Okay, so that's enough agony. So explain the solution, the quick and easy solution. I can prove to you real quick that there does not exist a tiling that hits all and only of these. Because what has to be the case about any individual tile? It covers both a black and a red square. Right? Now, notice what's true about both of the squares that have been removed. They're both red. Right? So any given tile must cover both a black and a red. That means that there are unequal numbers of black and red squares that need to be covered. That means that there is no tiling that covers all of this and only this. Clever, no? I never would have got this. I was just explained to me. I never would have sort of like gotten the insight. And apparently very few of the people in the study actually got this. A few of them did, but. So is the solution clear? No? Okay, so like, right, so any piece must cover black and red. And if you've removed two red pieces, there are now 32 black things on the board, but only 30 red ones. So since any given piece must cover both a black and a red, there is no tiling that will cover 32 black ones, but only 30 red ones. Okay, so the point of this is that it's not the kind of problem that you probably thought it was. So Kaplan and Simon found that when they asked people how they went about trying to solve this, they mostly framed it as a tiling problem, trying to find a pattern of tiles that would cover all and only the tiles. And that's not the right way to frame it because the search space is just ginormous. It's a humongous search space, and you're never going to get through it all. And that's what you'd have to do to prove that there is no tiling, right? But if you frame it in terms of this thing about how many black squares and how many red squares, there's a fairly straightforward solution. So that's an insight problem. It's a problem you're supposed to go, aha, at the end of it. That's the typical vocalization that they associate with it. But it's also a problem where you've shifted the way that you framed the problem. So you had it framed one way, and the solution appears only when you give up on one way of framing it and switch to another. And science is just full of these. Your daily life is also just full of these things. Like, this is the thing that makes you better than computers today, is that you can solve insight problems. You can reframe things. Computers, you pretty much have to give them the frame, right? You pretty much have to set the search space, you have to set the goal, and you have to set the available pieces. And if you don't tell it that stuff in advance, it can't even cope, it can't even start with the problem. But humans can. We can do this reframing stuff. Another kind of classic idea in psychology, this one goes way, way back, is Gestalt switches. So in solving insight problems, people experience what's called a Gestalt switch. Gestalt is your way of putting things together as a whole. It's classic. I hope you've all at least seen this before. You can see this both as an old lady facing sideways or as a young woman facing away from the thing. So this is either a chin with a mouth and a nose, or it's a neck with a necklace and the chin facing away. So everybody got that? Right. So in cases like this, the interesting thing is the way that you see the whole actually informs the way that you see the parts. So this thing that's either an ear or an eye, depending on which way you got it framed. Has everybody got at least the two ways of seeing this? Some people are shaking their head no. So the old lady, I'm going to trace out the face of the old lady. So she's got, this is her forehead, this is her nose, this is her mouth, and this is her chin. Okay? And the young lady, this is her chin, this is her nose, this is her ear. Yeah? Y'all got it now? Okay, good. So if you just got the other one, you've just experienced what's called a Gestalt switch. And it's probably not the case that you first started seeing, oh yeah, I guess that's a chin, and then moments later you saw that, oh, I guess that could be an ear. Typically it happens in like a flash, right? You switch quickly from one way of seeing to another, where your perception of what the whole picture is about actually informs your understanding of what each of its parts are. So this thing here could either be an ear or an eye, right? And your general view of the picture is what determines whether you see it as an ear or as an eye. Right? So again, this is an example of this thing that humans are really great at, is reframing. And it's an example of how the way that you have a situation framed informs not just like how you feel about it or something sort of ephemeral like that, how you actually see the picture is determined by your background or the sort of the meaning that you attribute to it and the kind of like the overall picture. So for any given part, how you perceive that part is crucially determined by how you perceive the whole. And this is going to kind of be the in. This is the in for how your broader worldview can influence the way that you see things that are right in front of you. And it's so convincing. When you're in one of these and you can't see the other, every aspect of it is so convincing. It's obviously an ear. How could you see it as anything but an ear? And then when you make the switch, I don't know how I could have ever seen that as an ear. It's obviously an eye, or something like that. This is designed to be like precariously balanced, two almost exactly equally plausible ways of seeing. Usually in a paradigm shift, you have one way of seeing and then you kind of shift irrevocably to the other way of seeing. But that's the basic idea. Right. So this is discovery, and this is the kind of cognitive character of discovery that makes it penetrable by values, right? Penetrable by the large view has a capacity. The large view is not only built up out of the pieces, it also helps to build the pieces, right? So your overall view and your view of the specifics are in this co-constituting relationship. Neither one is fundamental or prior to the other. They have to be building each other at the same time. So the scientific fact which jumps out at you is so obvious and so clear is at once the basic building block of your overall worldview and is itself constituted by that overall view. So to just briefly bring this back to more concrete stuff, this was Grinnell's insight problem that he talked about in this chapter. So this insight problem was something that looked like an ear, noise, turned out to be data, an eye, I don't know, whatever. So what he did was he creatively reframed the thing that he was looking at. Same system, same physical system, same causal properties, but he found a new way of looking at it. He creatively reframed the system in question, and that meant suddenly new tools and new paradigms became available. Things that were irrelevant became relevant, things that were relevant became irrelevant. And this is not just a scientific thing, it is the general character of human cognition. Neat, huh? Any questions? Okay, great. So next time we're reading Grinnell chapter 3, and we'll talk about the other half of this process, which is the credibility process. Thanks.